What if I told you that one of the most prescribed medications on Earth, a drug that prevents heart attacks and strokes in millions of people every single day, started its life as rat poison? Not metaphorically, literally. It was designed to kill, and it did, very effectively. But before it became rat poison, it was something else entirely. Something that was killing cattle by the hundreds on farms across North America in the 1920s. Farmers watched helplessly as their healthiest animals bled to death from the inside, and nobody could figure out why. Until one scientist received a package in the mail. Inside was a dead cow, a bucket of unclotted blood, and a farmer's desperate plea for help. What he discovered didn't just solve the mystery. It changed the course of modern medicine and gave us one of the strangest origin stories in pharmaceutical history. This is the story of how death became a cure. It's the winter of 1933, rural Wisconsin. A bitter cold February morning. A farmer named Ed Carlson has just lost another cow, the fourth one this month. Strong, healthy animals, and then suddenly, they're bleeding internally, collapsing, dead within hours. No wounds, no infections, just mysterious, unstoppable hemorrhaging. Carlson isn't alone. Across Wisconsin, North Dakota, and Alberta, Canada, farmers are reporting the same nightmare. Cattle are dying by the hundreds. Some bleed from the nose. Some collapse in the field. Autopsies reveal massive internal bleeding, but no one can explain why. The common thread? All of the affected herds had been feeding on sweet clover hay. Sweet clover was cheap, abundant, and normally harmless. Farmers had been using it for decades. But something had changed. In wet conditions, when the hay wasn't dried properly, it would spoil, and when cattle ate that spoiled hay, they died. Veterinarians tried everything. Blood transfusions, dietary changes. Nothing worked, and the deaths kept mounting. Ed Carlson had heard about a biochemist at the University of Wisconsin who might be able to help. So he did something desperate. He loaded a dead cow, a milk can filled with its unclotted blood, and 100 pounds of spoiled sweet clover hay into his truck. He drove over 200 miles through a blizzard, and he showed up unannounced at the university's agricultural hall with a single question. Can you tell me what's killing my cattle? The man who received that grim delivery was Karl Paul Link. Link wasn't a medical doctor. He was a biochemist, trained in organic chemistry, with a particular interest in plant compounds. He was methodical, obsessive, and had a reputation for taking on problems that other scientists found too messy or too obscure. This problem was both. Link examined the samples Carlson brought. The blood was strange. It refused to clot, even after sitting for days. That wasn't normal. Blood clots naturally, quickly, to prevent bleeding. Something in that hay was interfering with the clotting process at a fundamental level. So Link and his team began the painstaking work of isolating the compound responsible. They processed ton after ton of spoiled sweet clover. They ran chemical tests. They fed extracts to rabbits and watched their clotting times. Month after month, they narrowed it down, separating, purifying, testing. It took 6 years. In 1939, Link's team finally isolated the culprit, a compound called dicumarol. When sweet clover spoils, a natural substance in the plant called coumarin breaks down and transforms into dicumarol, a powerful anticoagulant that blocks vitamin K, which the body needs to form blood clots. Without vitamin K, blood can't clot. Cattle bleed internally. And they die? Link published his findings. Farmers learned to dry their hay properly or avoid sweet clover altogether. The cattle deaths stopped. Case closed, right? Not even close. Here's where it gets interesting. Link didn't stop at dicumarol. He realized something profound. If this compound could prevent clotting in cattle, it could prevent clotting anywhere. And if you could control the dose, carefully, precisely, you could make blood less likely to clot without causing uncontrollable bleeding. That was powerful, because in the 1940s, blood clots were, and still are, one of the leading causes of death worldwide. Heart attacks, strokes, pulmonary embolisms, all caused by clots forming in the wrong place at the wrong time. But Link also saw a more immediate, practical application. Rats. Rats were everywhere in post-war America, in cities, on farms, in warehouses, and they were nearly impossible to poison effectively. Traditional rat poisons were bitter, fast-acting, and easy for rats to avoid after the first animal in a colony got sick. What Link needed was something tasteless, odorless, and slow. something that would kill rats days after ingestion, so they wouldn't associate the poison with the bait. Dicumarol was too unstable. So Link and his team synthesized a more potent, more stable version. In 1948, they created compound number 42 on their list of anticoagulants. They named it after the organization that funded the research, the Wisconsin Alumni Research Foundation, WARF. Warfarin. By 1952, it was being mass-produced and sold as the most effective rat poison on the market. Farmers loved it. Pest control companies stocked it. It became ubiquitous. And for a while, that's all it was. Rat poison. Effective, cheap, and wildly successful. No one was thinking about putting it in humans. There's an old principle in toxicology, credited to a 16th century physician named Paracelsus. The dose makes the poison. In other words, there is no substance on earth that is purely a medicine or purely a poison. Everything depends on how much you take. Water can kill you if you drink too much. Oxygen becomes toxic at high pressure. Even vitamins, in massive doses, can cause organ failure. And warfarin, in large, uncontrolled doses, it causes fatal hemorrhaging. But in small, carefully monitored doses, it does exactly what Karl Paul Link realized it could do back in the 1940s. It prevents dangerous blood clots from forming. The question wasn't if warfarin could be used in humans. It was should it be? And more importantly, would anyone be willing to try? In the early 1950s, the medical community was deeply skeptical. Warfarin was rat poison. The idea of giving it to patients, even sick ones, felt reckless, dangerous, unethical. But then something happened that changed everything. In 1951, a U.S. Navy sailor attempted suicide by ingesting a massive dose of warfarin-based rat poison. He didn't die. Doctors treated him with vitamin K, the antidote, and he made a full recovery. The case was documented, studied, and published. And it proved something crucial. Warfarin's effects were reversible. That opened the door. Clinical trials began. Researchers tested warfarin on patients with deep vein thrombosis, atrial fibrillation, and post-surgical clotting risks. The results were undeniable. It worked. It worked better than anything else available. In 1954, the FDA approved warfarin for medical use in humans. And then, in 1955, President Dwight D. Eisenhower suffered a heart attack. His doctors prescribed warfarin to prevent further clots. The President of the United States was taking rat poison, and it was keeping him alive. After that, public perception shifted almost overnight. If it was safe enough for the President, it was safe enough for anyone. Warfarin became one of the most prescribed drugs in the world. Today, millions of people take it daily. It prevents strokes in patients with irregular heartbeats. It treats blood clots in the lungs and legs. It saves lives, constantly, quietly, all over the world. And it all started with a farmer, a dead cow, and a biochemist willing to spend 6 years figuring out why. So here's the thing about discovery. Sometimes it doesn't look like progress. Sometimes it looks like death, like failure, like a substance so dangerous that the only reasonable use for it is killing pests. But in the right hands, with the right dose, and the right understanding, poison becomes medicine. Karl Paul Link didn't set out to create a life-saving drug. He set out to solve a mystery, to answer a farmer's question, to understand why cattle were dying. And in doing so, he gave the world one of the most important medications in modern medicine. If you found this story as fascinating as I did, hit that like button and subscribe. We've got plenty more accidental genius coming your way. I'll see you in the next one.